Hi everybody. In this video, we're going to learn how to find the eigenvalues and eigenvectors. We're going to do 2 by 2 and 3 by 3 examples. Here are the steps. Let's begin. We were given matrix A, 2, 1, 1, 2. Our characteristic equation will be determinant of A minus lambda I equals the 0 vector. Here A is our original matrix, which is 2, 1, 1, 2. Lambda is the constant, the scale factor. I is our identity matrix, which is 1, 0, 0, 1. Here it is 2 by 2. And it's going to be equal to 0, 0, which is 0 vector. And if we multiply lambda by identity matrix, what we get is lambda 0, 0, lambda. And if we subtract A minus lambda I, which is going to be 2, 1, 1, 2, minus this will be 2 minus lambda, 0, 1, and 2 minus lambda. So technically, we can directly subtract lambda from the main diagonals. So what we did was subtracting lambda from each entry of the main diagonal, which is our step 1. Now let's do step 2. Step 2 is solve for lambda, but we need to take the determinant first. So now we're going to take the determinant of this characteristic matrix. So 2 by 2 determinant is easy. The right diagonal, product of right diagonal, minus product of left diagonal. So what we're going to have is 2 minus lambda times 2 minus lambda minus 1 times 1. This is going to be 1. If you FOIL here, distribute, you're going to get lambda squared. 2 times lambda is 2 plus times 2 is 4, which is going to be minus 4 lambda plus 4 equals to 0, which is 0 vector. And if you simplify, what you're going to get is lambda squared minus 4 lambda plus 3 equals to 0. Now we need to solve for lambda. This is quadratic, so we can factor it like lambda plus 3 times lambda minus 1. No, it's going to be lambda minus 3 lambda minus 1, because negative 3 times negative 1 is positive 3, and negative 3 plus negative 1 is negative 4. So this is the correct factoring. Now if we solve for lambda here, this is going to be lambda equals to 3, and here lambda will be equal to 1. So these are our eigenvalues. We found our eigenvalues. So step 1 and step 2 is finished, which helped us to find the eigenvalues. Now we're going to find the eigenvectors. To be able to find the eigenvectors, we're going to follow the recipe step 3. Our matrix is 2, 1, 1, 2. Our first step is to subtract lambda, one of the values. Let's say for lambda 1, let's find the vector, eigenvector for lambda 1. So we're going to subtract 1 from the main diagonal. The characteristic equation is A minus lambda I times vector x, which is our eigenvector, equals to 0 vector. So what we are doing here is actually this. This is our A minus lambda I times vector x, which is x1, x2, equals to 0 vector, which is 0, 0. And here, let's simplify. 2 minus 1 is 1. 1, 1, 2 minus 1 is 1. And this is x1, x2 equals to 0, 0. Now we're going to do row reduction, number 4, and then we're going to find the null space. And whatever vector we find will be our eigenvector for lambda 1. Let's continue. Now we're going to reduce. Now reduce. So our vector is 1, 1, 1, 1. So manipulate row 2, negative row 1 plus row 2. What we're going to get is 1, 1, 0, 0. So we did our row reduction. Okay, now we're going to convert this into equation. Here x2 is our free variable because there is no pivot here. And x1, 1x1 plus 1x2 equals to 0. Here, if we solve for x1, we're going to get x1 is equal to negative x2. And here, x2 is free variable, so x2 is equal to x2. And if we factor out x2, what we're going to get is negative 1, the coefficient here. This is negative 1 coefficient and positive 1 here. So this is our first null space or first eigenvector for lambda 1. So negative 1, 1 is the first eigenvector for lambda equals to 1. Now we're going to find the eigenvector for lambda equals to 3 value. So for lambda equals to 3, we're going to do all the same operations we did here. So our original matrix is 2, 1, 1, 2. So from our original matrix 2, 1, 1, 2, we're going to subtract lambda value from the main diagonal. And what we're going to get is negative 1, 1, 1, negative 1. Now we're going to do row reduction. Okay, so row reduction, if we add row 1 and row 2, so change row 2, add row 1 to row 2. So what we're going to get is row 1 stays the same and row 2 becomes 0, 0. Now we can write the equation here. Again, x2 is free variable because there is no pivot here. And here negative x1 plus x2 equals to 0 and x2 equals to x2. Here x1 equals to x2 and x2 equals to x2. If we factor out x2, we're going to get 1 is the coefficient, so we're going to get 1, 1. So 1, 1 is our next eigenvector for lambda equals to 3. So each eigenvalue will be corresponding to one eigenvector. So for lambda equals to 3, this is our eigenvector. So steps are the same for any dimension of matrix, 2 by 2, 3 by 3. All we have to do is to find the eigenvalues, and then after we find the eigenvalues, we're going to find each eigenvector for each eigenvalues following these steps. Let's go to 3 by 3 example. Our matrix is given 1, 2, 1, 2, 1, 1, and 1, 2, 1. Our first step is to find the characteristic equation, which is a minus lambda I equals to 0. This formula or this characteristic equation, you might see this like this. It could also be lambda I minus a equals to 0. You're still going to get the same answer. Okay. So this technically means subtract lambda, from each entry on the main diagonal. Okay, let's do that. So this is our original matrix, which is 1, 2, 1, 2, 1, 1, 1, 2, 1. And we're going to subtract lambda from the main diagonal. Why? Because lambda times I will be lambda 0, 0, 0, lambda 0, 0, 0, lambda. And if we subtract this from A, that's what we're going to get. Okay, now next step is to take the determinant. Take determinant and solve for lambda. Okay, so we can take determinant using many different techniques here at 3 by 3 matrix. I would like to use the row expansion. So I would like to expand row 1. Let me rewrite here so you can see clearly. 1 minus lambda, 2, 1, 2, 1 minus lambda, 1, 1, 2, 1 minus lambda. Okay, our first entry is 1 minus lambda here. So our determinant will be 1 minus lambda times determinant of this matrix. That's how we take the determinant by row or column expansion. So determinant of 1 minus lambda, 1, 2, 1 minus lambda. Minus, this is the I hat, which is positive, j hat is negative, k hat, so it goes positive, negative, positive, negative. So the second entry is 2 times determinant of, it is like this. So this is the second entry now. So 2 times determinant of this. We're going to merge it. So 2, 1, 1, 1 minus lambda. And finally, plus the third entry. The third entry is 1. 1 times determinant of this matrix. So it's going to be 2, 1, 1 minus lambda, and 2. Now I'm going to simplify this. So 1 minus lambda times determinant here is the diagonal product, which is 1 minus lambda times 1 minus lambda, minus 2 times 1, which is 2. Minus 2 times, the determinant here is 2 times 1 minus lambda, minus 1 times 1. And finally here 1 times the determinant of this matrix, which is 2 times 2 is 4, minus 1 times 1 minus lambda. So if you carefully distribute, and simplify this, what you're going to get is, so I'll leave the algebra part for you. So what you're going to get is negative lambda cubed plus 3 lambda squared plus 4 lambda equals to 0. If we factor out negative lambda here, what we are going to get is lambda squared minus 3 lambda minus 4 equals to 0. And we can factor out this quadratic as well. So it's going to be lambda plus 1, lambda minus 4. Here, the first lambda value will be equal to 0. Here, lambda will be equal to negative 1, lambda 2 equals to 1, and lambda 3 from this factor equals to 4. These are our eigenvalues. Now we're going to find the corresponding eigenvectors for this each lambda values. Let's go ahead and find the eigenvector for lambda equals to negative 1. Again, the order is not important for lambda equals to negative 1. Our original matrix is 1, 2, 1, 2, 1, 1, and 1, 2, 1. Our first step is to subtract this lambda value from each entry on the main diagonal, which is a minus lambda I. We're going to take the determinant, the vector x, which is eigenvector, equals to 0 vector. So our first step is to subtract the lambda value, which is negative 1, from each entry on the main diagonal. Okay, let's do that. So it's going to be 1 minus minus 1, 2, 1, 2, 1 minus minus 1, 1, 1, 2, and again 1 minus minus 1. So what we're going to get is 1 minus minus 1 is 1 plus 1, which is 2, 2, 1, 2, 2, 1, and 1, 2, 2. This is what we're going to get. Now, row reduction, or row reduce and find the null space. Okay, so we're going to find the null space by row reduction, and then what we find will be our eigenvector. So as our first step, we can change row 2 by negative row 1 plus row 2. So 2, 2, 1, 0, 0, 0, 1, 2, 2. Here we can switch row 2 and row 3. So what we're going to get is 1, 2, 2, 0, 0, 0. Here we can change row 2, subtract negative 2 times row 2 plus row 1. And what we're going to get is row 1 doesn't change, row 3 doesn't change, and row 2 will be negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 2 is negative 4 plus 2 is negative 2. Negative 2 times 2 is negative 4 plus 1 is negative 3. Now let's work on row 2. Let's multiply row 2 by negative 1/2. So we're going to get our first pivot. So 0, 0, 0, 0. Negative 2 times negative 1/2 is positive 1, and negative 1/2 times negative 3 is positive 3 over 2. Row 1 did not change. Now we can change row 1 by negative 2 times row 2 plus row 1. Row 2 and row 3 did not change. Row 1, negative 2 times 0 is 0 plus 2 is still 2. Negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 3 over 2 is negative 6 over 2. Minus 1 will be negative 2. because it's going to be negative 4 over 2. Okay, this time row 1, let's multiply everything on the row 1 by 1/2. So what we're going to get is 1, 0, negative 1, 0, 1, 3 over 2, 0, 0, 0. This is our reduced matrix. Now we're going to find the null space. This is like x1, x2, x3, a times x equals to 0. From the first row, we get x1 plus negative x3, which is x1 minus x3, equals to 0. From here, x1 equals to x3. From the second row, x2 plus 3 over 2x3 equals to 0. We get x2 equals to negative 3 over 2x3. And the third row, x3 is the free variable because there is no pivot here. So x3 equals to x3. Here in this equation, if we factor out x3's, what we're going to get is the coefficients. So the coefficient is here 1, here is negative 3 over 2, here is 1. So 1, negative 3 over 2, and 1 is our first eigenvector. So this is the eigenvector, first eigenvector for lambda equals to negative 1. So each lambda value corresponds to one eigenvector. Now let's go ahead and find the other eigenvectors. We have lambda equals to 0 as the eigenvalue. Let's go ahead and do that. So for lambda equals to 0, our original matrix is 1, 2, 1, 2, 1, 1, and 1, 2, 1. So we're going to subtract the eigenvalue from each entry on the main diagonal. So this will not change the matrix because 1 minus 0 will be still 1. So we're going to reduce this matrix. Our first step is change row 3, row 1 minus row 3. So what we're going to get is 1, 2, 1, 2, 1, 1, and 0, 0, 0, because it's identically the same. Our second step is to change row 2. Negative 2 times row 1 plus row 2 will be helpful. So what we're going to get is row 1 is not changing, row 3 is not changing, and row 2 will be 0, negative 3, negative 1. Now we're going to change row 2. We can multiply everything on the row 2 by negative 1/3. So we can get our first pivot. Row 3 did not change, row 1 did not change. Row 2 will be 0, 1, and it's going to be 1/3 positive. Now we're going to change row 1 again by negative 2 times row 1 plus row 2 plus row 1. So here we're going to get 0, 0, 0. Row 3 did not change, row 2 did not change, and row 1 will be negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 1/3 is negative 2 over 3 plus 1 will be 1/3. So this is our reduced matrix. Again, this times x1, x2, x3 from our characteristic equation equals to 0 vector. From the first row, we get 1 times x1 plus 1/3 times x3 equals to 0. Here, x1 equals to negative 1/3 x3. From the second row, we get x2 plus 1/3 x3 equals to 0. And from this equation, we get x2 as negative 1/3 x3. And our x3 is the free variable because there is no pivot here. So free variable. So x3 will be equal to x3. And if we factor out x3's here, we can find our null space. So x3 negative 1/3, negative 1/3, the coefficients, and 1. So this is our second eigenvector. So this is our eigenvector for lambda equals to 0. We found our second eigenvector too. Let's go ahead and find our last eigenvector. Okay, this time we're going to work for lambda equals to 4. Our original matrix is 1, 2, 1, 2, 1, 1, and 1, 2, 1. We're going to subtract 4 from each entry on the main diagonal is our first step. So 1 minus 4, 2, 1 stays the same, 2, 1 minus 4, 1 stays, and 1, 2, 1 minus 4. So what we're going to get is negative 3, 2, 1, 2, negative 3, 1, 1, 2, negative 3. Now we're going to reduce this matrix and find the null space. Okay, let's do it here. Negative 3, 2, 1, 2, negative 3, 1, 1, 2, negative 3. Our first step is to change row 3. 3 times row 3 plus row 1. So what we're going to get is row 1 does not change, row 2 does not change, and row 3 becomes 0, 8, negative 8. Now our second step is to change row 2. 2 times row 1 plus 3 times row 2. Row 3 does not change, row 1 does not change, and our row 2 will be 0, negative 5, positive 5. This time we're going to change row 3. 8 times row 2, you have to do operation between row 2 and row 3 here, because if you do operation between row 3 and row 1, you gain value again to 0. So 8 times row 2 plus 5 times row 3. So row 1 and row 2 did not change, so let's go ahead and write directly. And here we get 0, 0, 0. This was negative 8, by the way. Okay, our next step is to make row 2 all ones. So we're going to get our first pivot by modifying the row 2. So negative 1/5 times row 2 will gain us 1. So it's going to be negative 3, 2, 1 did not change, 0, 0, 0 did not change, and negative 1/5 times 0 is 0, negative 1/5 times negative 5 is 1, and this is going to be negative 1. This time we're going to change row 1. Negative 2 times row 2 plus row 1. And we're going to get, let's write whichever did not change. So 0 times negative 2 is 0, plus 3 is negative 3. This is going to be negative 2 plus 2 is 0. And negative 2 times negative 1 is positive 2, plus 1 is positive 3. Now, this is the last operation. We're going to multiply everything on the first row by negative 1/3. And what we're going to get is negative 3 times negative 1/3 is positive 1, 0 times that is 0, and 3 times negative 1/3 is negative 1. This is our reduced matrix. Now, x1, x2, x3, we're going to find the null space. Okay, from the first row, our equation is 1 times x1 minus 1 times x3 equals to 0. And from the second row, we have x2 minus x3 equals to 0. And our third row is x3 equals to x3 because it's the free variable. x3 is the free variable because there is no pivot here. Now from the first equation here, we solve x1 as negative x3. From this equation, we solve x2 as, this is going to be positive x3 because add x3 to both sides. And again, this is going to be x3 and x3 equals to x3. And if you factor out x3, you can find your null space. So all the coefficients are 1. So 1, 1, 1 is the last eigenvector, which is corresponding to for lambda equals to 4. This is the eigenvector. So that's it for today. Let's sum up and finish. So we find the eigenvalues, and after finding the eigenvalues using the steps I have given at the first part of the video, we find the eigenvalues, and then we go ahead and find the eigenvectors by subtracting the eigenvalue from the main diagonals, and reducing the matrix is the second main step. And after the reduction, you need to find the null space. So to be able to be very fluent at eigenvalues and eigenvectors, finding the determinant is prerequisite. You need to be very good at finding determinants, 2 by 2 and 3 by 3 matrix. So you need to practice determinants very well. And then you need to practice how to find the null space. So these two elements will gain you power to find eigenvalues and eigenvectors. See you at the next video. Thank you for watching.